Okay, so right now I want to go over what you guys missed in class. So I'm going to kind of really quickly talk through this. It's probably a good idea for you to pause as I'm going through this to think about some of these answers before I tell you the answer. So this is the question of the day. This person's accelerating because they're speeding up. This person's accelerating because they are slowing down. This person's accelerating because they're changing direction. Acceleration just means a change in velocity. If you remember from when we talked about velocity before, velocity is both speed and direction. So if you change your speed, you're accelerating. Specifically, this one we call deceleration if your speed is getting lower. And then this one, because velocity is speed and direction, if you change your direction, you're still accelerating. Okay, next slide here. What we did right here is talked about the definition of acceleration and the units. So I'm going to really quickly go here and write in what we did here. So the definition of acceleration is an increase or decrease in speed or change in direction. And the units of that, unfortunately I can't write out very well here, meters per second squared. So that 2 really should be the superscript, and I don't remember off the top of my head how to make that actually on Google Sheets, but it should be meters per second squared. A little bit later, when I recorded my iPad on the board, I'm going to have a little bit more discussion about what that actually means, so I'll probably try and sneak that in here somewhere. Hey guys, I wanted to record a quick video of what you missed in class today. So this is some of the board work that we did. Acceleration can be a pretty tough concept to wrap your brain around, so I did it in a very slow manner in class. I think everybody understood at the end, but you guys are going to be behind by missing this, so hopefully this helps get you caught up. So the first thing, this is from the first slide that we looked at after the question of the day, was the idea of what the units of acceleration are. Well, the units of acceleration are meters per second squared. I'm actually skipping the definition because that's really what the question of the day was about. The definition of acceleration is just change in speed or change in direction. So the units of acceleration are meters per second squared, but that's kind of weird because usually when you hear about a square unit, you think about meters squared or feet squared or something like that, and that makes sense because that means it's a height and a width or a length or something like that, but you can't do that with time. So the idea of a square second is kind of strange. So what we actually do is to help us think about that, I'm going to expand that expression of a second squared to seconds times seconds. And I've kind of intentionally stretched that out there so you can see that what acceleration really is. Meters per second component, that's the velocity. It's how much that meters per second is changing every second. So another way to think about it is meters per second per second. So it's basically how much is your meters per second changing every second. That's where that second comes from. Right there. So in the moving man example, it is how much every second do I get faster by or do I get slower by? So I'm going to pause this and put this into our... So we use the moving man to illustrate this concept. So I put this application, this simulation on the Haiku homepage. If you want to try and download it and simulate what I'm doing, it's not a terrible idea. So first scenario on this sheet here, which I attached to the email, if I start the moving man with above parameters that's at 0 meters, the velocity of 0, and an acceleration of 1, what will their velocity be after 1 second, or after 2 seconds, or after 3 seconds? So you can go ahead and fill this in right now if you want. Maybe pause the video and think about that. Probably won't make as much sense because I skipped over that units part earlier, but you'll catch on. So I've set up those parameters. I go ahead and I press play, and I'll go ahead and sorry, I hope that didn't scare you. I'll go ahead and play that back, and you'll notice after 1 second their velocity is 1. After 2 seconds, the velocity is 2. After 3 seconds, the velocity is 3. So starting from rest at a velocity of 0, what 1 meter per second squared means is that every second you're getting faster by 1 meter per second. So let's go back to this file here. So if I did acceleration of 2 meters per second, what would it be after 1 second, 2 seconds, or 3 seconds? So let's clear that and set this back here, 0 and 2 meters per second. So like I said, you might want to pause it before this. Let's go ahead and play this back, and we've got 2 meters per second, 4 meters per second, and 6 meters per second. So once again, an acceleration of 2 meters per second squared means that every second your velocity is changing by 2 meters per second. And so if we started from 0 meters per second, it should go 2, 4, 6 after every second. Okay, going back here, this one's a little bit of a trick one. If you have an initial velocity of 3 meters per second and an acceleration of 0, what would your velocity be after 1, 2, and 3 seconds? I'm going to start them back a little bit further this time. And hit play. Oops, I need to clear that, my bad. -10, 3, okay. So what you should hopefully notice is that this guy is traveling at a constant pace at 1 second, at 2 seconds, at 3 seconds. At all of these times, his velocity is 3 because an acceleration of 0 means he's not changing his velocity. Going back here, if you start with an initial, that word initial just means first or in the beginning or at the start. So right away, right off the bat, he's got a velocity of, let's start at -10 again. He's got a velocity of 3 and an acceleration of 1. Let's go see what that looks like. Okay, so after 1 second, he was going 4 meters per second. After 2, he was going 5. After 3, he should be going, oops, 3, he should be going 6. So once again, if you started at 3, every second you get faster by just 1 meter per second overall. Okay, let's head on back. This is the one that brings into the idea of deceleration. So deceleration is acceleration in a negative direction. So, or opposite from your original direction of motion. So position of -10, velocity of 3, and an acceleration of -1. So now if I hit, oops, sorry guys. Now if I hit play, okay, so let's play that back. After 1 second, he was only going 2 meters per second. After 2 seconds, he's going, round that up to 1. After 3 seconds, he should come to a complete stop. And if that keeps on accelerating at -1 meters per second squared, what that means is after 4 seconds, they're actually going negative. They're going to the left. That's why velocity direction matters. He's going the exact same speed here and right here, where he's got 1 meter per second for his velocity, but he's got different velocity because in this one he's going to the right. At 4 seconds, he's going to the left. And finally, the last example is if they've got an initial velocity of 6 meters per second and a constant negative acceleration of -1.5 meters per second squared, how long does it take for him to come to a complete stop? Once again, you might want to stop this and make that prediction about how long that would take before you see me do that. So let's head over here and clear and start at -10 again. Velocity of 6, acceleration of -1.5, and let's play that. Okay, and he came to a stop at, if I play that back, right at 4 seconds. That's how long it took for him to come to a complete stop. And the follow-on part of that was after 5 seconds what his speed would be. It is negative 1.5 meters per second. So what I'm going to do right now is I'm going to use my iPad to record a little bit of work on the board because ultimately we're not going to just do this conceptually like I was just doing. Ultimately you're going to have to solve this kind of a problem right here using algebra, using an algebraic formula. So that formula is on this next page. It's this one right here. I'm going to not go into detail about what that is right now, but it's A equals VF minus VI over T, that formula. Okay. Okay, so you should have just watched me go over the moving man idea. I'm going to tackle that last question, question number 6, using some formulas. So that formula is A is equal to VF minus VI over T. VF stands for the final velocity. VI stands for the initial velocity. Once again, that just means the velocity at the start. And T is your time, A is your acceleration. So in question number 6, let's make sure I get a good marker. In question number 6, the A, that acceleration was negative 1.5 meters per second squared. The velocity initial, I said it started at 6 meters per second. We're looking for the time, so we don't know that. And if you read that question carefully, I said that I asked for how long it would take an object with an initial velocity of 6 meters per second and an acceleration of negative 1.5 meters per second squared to come to a complete rest. Well, rest is stopped. So what I'm ultimately asking for is when does the velocity final become 0 meters per second? So when we solved this before on the video, what I said is that it takes ultimately 4 seconds for that object to come to rest. And we did that kind of conceptually or logically. But now we need to do it algebraically. I want you to see how we get this answer. So I'm going to rewrite what we just got here. So I'm going to plug everything in. Negative 1.5 meters per second squared is equal to 0 minus 6 meters per second divided by the time. Hopefully that's all catching on there. And we can instantly just get rid of the 0 because that's just inconsequential. And our first step in solving this equation is to multiply both sides by t. If we want to solve for t, you got to get t in the numerator. So that cancels over there, leaving us with negative 1.5 meters per second squared times t is equal to negative 6 meters per second. So your final step now here, I'm going to use another different color. Algebraically, divide by negative 1.5 meters per second squared, divide by negative 1.5 meters per second squared. That all cancels out over here. The negatives turn into positives. 6 divided by 1, so t is equal to positive 6 divided by 1.5 is 4. Meters cancel out. You've got seconds divided by seconds squared. That actually brings that into the numerator and cancels out one of the s's, giving you t is equal to 4s, 4 seconds. So what I want you to see there is that I got the same answer. 4 seconds, that's the same answer we got logically using that moving man. But we used the 3 variables that we identified, we plugged them into the acceleration equation, and we solved for time. So ultimately, we're going to be solving most of our problems algebraically like this, which can sometimes be a little bit more difficult to kind of wrap your brain around compared to looking at the moving man. But ultimately, when you start dealing with variables like an acceleration of negative 9.8 meters per second squared, that's the value of gravity, or if you have a time of 7.19 seconds, or let's say that your final velocity is 38.59. I'm just realized I'm writing all of this off the screen. Let me rotate this a bit. ultimately, if you have values for your variables like this, you are not going to be able to just logically solve it and think, okay, after 1 second it'll be traveling this fast, and after 2 seconds it'll be traveling that fast. So that's why it's really important to be able to plug these kinds of variables into an equation like that. I hope this helped you guys. I'm sure you'll still be a little bit confused compared to kids from class, but let me know what questions you have.